Hello, everyone, and welcome to the Mastering Design Complexity in Onshape series of presentations. Today's presentation, a deep dive into surfacing. We're really going to dive into the depth of surfacing, understand the core fundamentals of surfacing. My name is Cody Armstrong. I'm the Senior Director of Technical Services here at Onshape. And unfortunately, Greg Brown won't be able to join us today. He's having a technical issue with his internet. So it'll just be me solo today. And we're really going to dive into surfacing as a whole. For those interested in a more complex discussion around surfacing, this is your presentation. So without further ado, let's get started. Now, I mentioned introductions. Unfortunately, Greg won't be able to join us here today. And what I'd like to do is start with what is the Mastering Design Complexity webinar series. And it's a series of presentations we're putting together to talk about the more advanced topics that we have in Onshape, and really try and drive home not just a feature-based approach to our presentations, but a more workflow and process-oriented discussion around some of the more complex aspects of designing in Onshape. And we really want to take this opportunity to highlight examples of advanced techniques, common practices, and also pitfalls to avoid. And we're going to cover all of those in today's presentation. So we're going to go into some advanced techniques for servicing, some common practices to keep in mind when creating surface models, and also pitfalls to avoid, things you want to avoid to save yourself some time and some headache when modeling. And as I mentioned before, this is really a focus broader than features. We really want to expand the scope of what we're talking about beyond, the traditional webinars that we've done in the past that describe kind of the clicks and the features themselves and are very prescriptive. What we're trying to do here is take a step back and focus on a broader process or workflow that you would want to take to accomplish, the examples that we show here. And so this is going to be a bit different if this is your first Mastering Design Complexity webinar. This is a little bit different than what we do in some of our other webinars. They're a little less prescriptive, but we're going to take a look at some good examples of geometry, in this case, surface models, and what makes them good, what practices were followed that makes them a good example. And so that's the idea behind the Mastering Design Complexity webinar series. It's really a focus on advanced topics, advanced techniques, common practices, pitfalls to avoid, but on a broader context than a more traditional webinar that's feature focused. So what is today's topic? Well, today is a deep dive into surfacing, and surfacing is its own sub-tangent within professional CAD systems, and there's a lot of knowledge that you need to know in order to really dive into it. So the first question that I want to take a moment to get into, and we'll get into in a second, is what is surfacing and do I need it? So if you're new to surfacing, why would you need it? Or maybe you aspire to do surface modeling, but you haven't, or you need it for an upcoming project. Is this something I really need? And that's a question that we get quite often. So we're going to dive into that. Also, what is Onshape surfacing toolset? And I think that you'll be surprised. I have a handful of slides here that show the depth of Onshape surfacing tools, and it is genuinely a lot more than I think a lot of people think of. And I want to take a moment to highlight the huge tool set for surfacing that we have. And we're really only going to scrape the surface when it comes to the surfacing tool set that is available in Onshape. So we're going to spend a bit of time on this tool set, but I really just want to emphasize it's a lot, and there's a lot there to dive into. I also want to introduce the concept of the 10 golden rules. Now, the 10 golden rules aren't specific to Onshape, but they apply to Onshape. And so if you've come from other applications that are professional grade surface modeling applications, this is not a new concept. The 10 golden rules apply to really any kind of surface modeling, but they also apply, importantly, to Onshape. And so we're going to spend a fair amount of time going through and highlighting those 10 golden rules and how you can apply them in surface modeling. But in general, they're guidelines or philosophies for designing surface models that give you the highest quality surface models. So we're going to spend a bit of time and the 10 plus golden rules. And it's the 10 golden rules that are kind of traditional industry standards. And we have a handful of rules of our own that we think would help as well. And as always in the Mastering Design Complexity, it's all about the example models. And we're going to bring up an example model, walk through it, highlight what we think makes it really unique and well built, and highlight some of those good practices that we want to show. And I also have a number of tips to end things today. So there's going to be kind of a speed run of surface modeling tips at the end of the presentation today, really trying to drive in as many of those common surfacing tools and workflows as possible before we wrap things up here today. So what is surfacing, and do I need to use it? This is a commonly asked question, probably one of the most popular questions that we get asked. And to put it in a single sentence, it's surface modeling is commonly used to create complex freeform shapes. And so if the bulk of your modeling is prismatic modeling, you may not have a lot of experience with surface modeling. But I will say it's not only for creating complex freeform shapes. There's lots of applications for using surfaces as tools in solid modeling, even in one, two feature scenarios. And I think a lot of people view surface and solid modeling as mutually exclusive, right? And it's important to understand surfacing is not mutually exclusive with solid modeling. They're interwoven in a lot of ways. And so it's important to stress, as you're, considering this, not to think of it as an either or, like a one or the other decision. Oftentimes it's going to be a combination of both, and it just depends on the scenario and the tools that are best suited to solve whatever problem you're in front of. So just keep in mind, I think that a lot of users out there either know surfacing really well because their role requires it, or they stay away from it because it fits some definition that they don't feel they meet. And I think for a lot of users out there, surfacing can be a really powerful tool, even if all you do is, the majority of what you do is solid modeling. There's lots of great examples of using surface modeling as a tool for your solid modeling techniques. And do I need to use it? Maybe. There's a lot of applications for it. But since you're here today with us, my guess is that yes, you either use it today or you aspire to use it, and both are great. This is going to be a great presentation for you. So that's a simple explanation into surfacing. The big takeaway I would say is, even if you don't use surface modeling a lot today, there's a lot to be learned in general practice and even solid modeling techniques. So does Onshape do surfacing? Well, of course, Onshape has a huge library of surfacing tools. And I want to start with a simple explanation of kind of the core tools that everyone's familiar with, extrude, revolve, sweep, and loft. And if you're new to Onshape, it's important to stress, we've built all of these tools into one feature. So it's a little different than some other CAD systems that exist out there where they have a surface extrude and a surface loft and a swept loft. We have a sweep feature. And in that sweep feature, you can either create a solid sweep, a surface sweep, or a thin sweep. And so you can think of our surfacing tools at the core level as an option within that core feature, whether it be extrude, revolve, sweep, or loft. And so just keep in mind, if you're looking for a surface extrude button, what you're really looking for is the extrude feature and the option for surface within that. And that's true of all the kind of core features that exist in Onshape. Now, there's a lot of surfacing and curve specific features, and you're going to see a big emphasis on not only surfaces in this presentation, but curves as well. And this is a long list of features. These are just some to highlight. Now, I have brought in an even longer list. This is 38 surface or surface curve related features that have been added in roughly the last 2 years or so. And so we've been on a real push to build surfacing features into the product in a way that allows you to accomplish just about anything. And I think that's the message that I really want you to take away is this is the effort in just the last 34 releases or so, right? 2 years roughly. And so it's impressive. And I think a lot of users, if you haven't touched surfacing, if you haven't spent a lot of time in Onshape surfacing, know that the tool suite is very robust. And at this point, we've really gotten some exceptional tools available to the users out there today. So does Onshape do surfacing? Absolutely. Not only do we do surfacing, but we have a huge library of surface tools to allow you to build anything you need. So what about that tool set? Well, you kind of break it down into subsets. There are different subsets of tools depending on what you're trying to do. And we're going to focus on a handful of these today, some of the more cherry picking some of the more important ones for our workflow discussion. But this is how I would break up the different surfacing and curve features. And they're broken up into wireframe, surfaces, manipulation of those surfaces, and diagnostic tools to diagnose those surfaces. The wireframe, we'll get into this in just a moment, is a good surface model is built around a good wireframe. And those tools are things like the 2D Bezier sketch, 3D fit spline, bridging curve, projected curves, a whole bunch of curve features, because you'll find, and I'll say this probably multiple times throughout today's presentation, curves are the important core, the foundation for good surface modeling. And so if you can build a good foundation, you're much more likely to have a successful surface model as a result. So wireframe tools, long list of wireframe tools. We're going to dive into some of those today. But if you're looking for a handful of screenshots to take from today's webinar, this is definitely a good one. We, of course, have a long list of surfacing tools, core surfacing tools that are available, and a long list of manipulation tools. These are tools to manipulate those surfaces that you create, offsets and boundaries, replace face, a really popular one. I'm not going to have time to go through all of those today, but if you're just looking for what tools do I need to get started with surface modeling, these are definitely the tools to take a look at. Finally, diagnostics. Diagnostics is an important part of surface modeling. You want to constantly be diagnosing and analyzing your surfaces and your curves before you start building on top of them. And that's an important lesson that I want to people to take away from this presentation is you constantly be analyzing, constantly be diagnosing those surfaces and curves before you move on to the next step. And if you do that, you save yourself a lot of headache later on. And Onshape has a phenomenal set of diagnostic tools available to you. And I'm going to highlight a handful of those today as well. So those are the tool sets. Now, the 10 golden rules, I mentioned screenshots that are worth taking for this presentation. This is definitely one of them. I think that this would be one that might even be worth printing and putting it on your wall in your office, because it really is like the fundamental rules associated with surface modeling. And I mentioned this before, this is not specific to Onshape. It's really any professional grade CAD system that can build surfaces generally follows these rules. And so what are they? Well, good flow of control points, and control points as a whole, controlling them, minimizing them, is very important to well-built surface models. And so in general, you want consistent, even flow between control points as a baseline, for building your surface models. You also want to minimize the number of control points. And I'll go over examples of this in a moment. But in general, you want to have the fewest number of control points possible and increase only as far as you need. And that's a very important tip that I would take away from this is, I think it's very easy in a lot of these situations to add a whole bunch of control points, but remember what you're adding is increased complexity, inability to control the overall end shape, or you lose that ability to control the end shape. And in general, one huge takeaway is clean curves and clean surfaces are clean final products, and they just mean a lot less headache, right? And so minimizing the number of control points, a good flow of control points, two very important tips when building good surface models. Also, whenever possible, use single span curves. That's just creates simpler geometry, simple transitions between whether it be surfaces or other curves. Use single span curves whenever possible. Now, another one, the transition between curve and face, or face and face, you want to ensure tangency across center lines. And one of the biggest tips that I have for you is in surface modeling, but in general in parametric CAD, but especially in surface modeling, exploit symmetry whenever possible. Using mirror is a huge advantage if you have any kind of symmetry, because you just eliminate a whole subset of tangents that you have to find, or control points, or other relationships that you have to find. So it sounds simple, but keep in mind you should be using symmetry in any place possible, and it's especially important when building good surface models. The next tip: aim to create four-sided surfaces, and that's because of the nature of the tools that we're using to build them. So if you have a four-sided surface, boundary surface is probably your best bet. That will create the cleanest surface for you in most situations. Loft will also work, but Loft is directional. We'll get into that in just a bit. And the last tool that I would choose in that scenario, boundary surface loft, is fill. And fill can patch, so to speak, or fill insided surfaces, but you will end up with the resulting surface won't be quite as clean as if you had used a four-sided surface and something like a boundary surface. So in general, the advice is aim to create four-sided surfaces if possible, or a trim to achieve that number of surfaces. So both are really a very important part of the workflow, is creating the surfaces that are the trimming to create the surfaces that control the boundary the best. So jumping back, number 7, build to theoretical edges. And that means you want to build big surfaces and pull them back to manage your transitions or your blends. And you'll hear the concept of like kind of overbuilding your surfaces and then trimming them back to create the necessary blends between those surfaces. And that's an important thing. You don't want to build up to the transition. You want to build past the transition and trim back and create your bridging curves or whatever the feature might be that handles that blend. But build to theoretical edges when you're building those initial surfaces. You'll see an example we refer to as slab surfaces. You want to overbuild them to a certain extent, and then trim them back to manage those blends. Set construction tolerances at the start of modeling. I think that's a common practice across the board. And then avoid building from trimmed edges. And you probably hear me say this a few times throughout today's presentation, but avoid building lots and lots of features that are dependent on a trimmed edge. And there are other tips around trimmed edges that I'll mention in just a bit. But as a practice, you want to avoid those and have trimmed edges as far down in the feature list as possible, and avoid as much as you can the dependencies on trimmed edges and building lots of relationships to trimmed edges. And then, matching curves on the opposite side. And it really is all about rule number 1, the flow of control points. And I think, matching those curves on the opposite side is an important point when you're building those transitions between faces. The control point flow and the transition between them is, of course, very important. And to summarize it, the golden rules are your golden ticket to the highest quality surfaces. I think if you follow these 10 rules and you're as rigid as possible about conforming to these rules, you will in the end up with the model that is the cleanest in terms of its geometry. It's the most robust in terms of its ability to manage change. And in general, it's just the best practice for surface modeling. And so these are all tips, the 10 golden rules that you might even be worth printing out and putting up on your screen or on your wall in your office, because I think that they're good reminders of things that we deal with in surface modeling all day long. So what does this look like in practice? Well, let's dive into an example. And I'd like to dive into this engine cover. This is a model Greg put together. It's an engine cover for an RC car, and it has some aesthetically defined features, and it also has some mechanically defined features, which we'll cover later on. But how would you go about building this using surface modeling tools? And what are some techniques or tips that we can learn for building something like this using Onshape surfacing? And one of the first things I would stress, and it's mentioned this before, is golden rule 1 through 5 and 7, wireframe layouts, curve building, modeling to theoretical edges, right? And then using clean surface geometry. These are all examples. This initial shape is built using those tools. Now, notice this is a half of the engine cover. So we're using symmetry. We're using a wireframe layout that consists of both 2D sketches, right, and 3D curves. So we're building that wireframe layout using a combination of both 2D sketches and 3D curves. And we're building it out to theoretical edges. And so it's important to stress this, of course, I'm just going to jump back one slide here, is not a sharp corner in the corner of the engine cover. But we're building to that sharp corner, and then we're going to trim back and manage that transition as a separate feature. And so when we talk about building to theoretical edges, that's what we mean. Extend those surfaces out until they meet at that theoretical point, and then trim them back to manage your transitions around the surrounding faces. So What does this look like in practice? Well, let's dive into a quick example. And what I'd like to do is jump into the slabs example of this and first start with the wireframe. And I stress this because, I'll say this a handful of times, the curves are really the foundation of a good surface model. If you spend the energy in building out, well-constructed curves, you build a foundation to build your surface model well, right? That behaves well to change, that has, smooth continuity and all the things that we really desire in a good surface model. Now, this, I would like to stress, is actually a combination, I mentioned it in the slide there, of 2D sketches, right? A handful of basic 2D sketches, as well as 3D curves. And this actually uses a very neat feature called control point curve. If you're into building surface modeling and you're not using control point curve, definitely add it to your toolbar. I can't recommend it enough. There are a number of custom features I'll highlight in just a bit, but control point curve is one of the more useful ones for sure. And so what we've done here is essentially build a handful of 2D sketches and a couple of 3D curves that define the wireframe for that initial slab series of faces, right? And what I'd like to point out, a good organizational technique, going back to our past presentation on design intent, is notice the color of the geometry. The 2D sketches are blue, the 3D curves are this orange color. It's a very good practice. It's actually something we recently added, is to delineate those things with colors. And if you delineate your geometry, your curves from your sketches with colors, it makes looking at geometry like this, which is a wireframe layout of, kind of a half section of this engine cover, it makes it easy to understand. And if everything's the same color and you start adding more and more sketch geometry and curves, it can be very difficult to discern which is which. And so one big tip that I have for you is, add those colors to define whatever color scheme you define is most useful to you. Define the colors of the geometry and as a way of delineating them, and as a way of, at a glance, like we're looking at it here, I can tell the difference between the 2D sketch geometry and the 3D curves. And while this is only a handful of pieces of geometry, if this had dozens of pieces of geometry or even hundreds, you would really struggle to discern kind of from the wireframe fog what is what, right? And so that's where I think colors are really applicable. Now, the other thing I really want to stress is this is the beginning of this engine cover model. We're building the wireframe for all of the surfaces that will follow from it. So if I roll down into the slabs folder, you'll see we do a handful of features. We have a handful of boundary surfaces, and the boundary surfaces are just using the edges of the 2D sketch and the 3D curves, the control point curves in this example. So we have two boundary surfaces, a loft for that transition phase, and then a boundary surface here on the end. And so all we're really doing here is, the work really in this is defining those sketches and curves. Once we have that, it's just a matter of selecting the boundary surface and then selecting the individual edges that make up each boundary surface. And you can think of, surface modeling a lot of times, not always, as a process of building models face by face. And that's really what we're doing here. We're constructing these using a series of boundary surfaces or loft features. But the most important takeaway from this example that I would give you is spend extra energy constructing that wireframe layout building the proper design intent into the wireframe layout. And then the boundary surfaces will just sit on top of that. And so curves are everything. It's something I'm going to say a few times here today. So that is the first, rules that I would give you is, use those wireframe layouts, use the 3D curves, minimize the control points in all of those. Those are all single span curves, very simple to create, and also have kind of the minimum in terms of complexity to define their shape. So build those slab surfaces first. Also overbuild them. I mentioned that this is not how this will look, of course, in the end. It's not going to have this sharp corner that you see on the end here. We're going to have a transition. And so what we've done is overbuild, and now we're going to trim those back. So the next tip, use bridging curve. Bridging curve is a hugely powerful tool, and one that I think is underused even by surface modeling experts, because it has so many applications and so many potential uses. But there's a handful of things I would point out about this. Bridging curve is a very important tool for building those wireframe transitions between faces. And so you can see in this example, we've essentially taken those slab surfaces that I've constructed that make up that half of the engine cover, and we've trimmed them back. And I'm going to show you in a moment a few tips that we have, a few techniques that we have around trimming those surfaces. But we overbuild, trim back to the points of transition, right? And then we build those transitions using bridging curve. And bridging curve has all kinds of really neat features. It has the ability to match curvature and even flow with G3 continuity. So you can define, as smooth a transition as you could possibly want using bridging curve. And it creates a single span Bezier curve. And that's an important thing. That's one of the reasons we emphasize bridging curve, is because they tend to be very clean curves. The resulting curve tends to be very clean. And so it makes a great boundary for a boundary surface or a path or a profile even for things like a loft. And important to any parametric CAD system, but important to building good models, it's parametrically driven. It's referencing the geometry that's surrounding it. So if the surrounding geometry changes, naturally your bridging curve will update. It will update in a way that's predictable. And so I would say it's important to keep in mind, as you're doing this, the transitions are especially important. So let's take a look at an example of this. Let me dive in here. I'm going to jump into my next tab, just a few steps forward. And there's a few things I would point out about this, just to set it up a little bit before we dive into the nuances of the bridging curve. So if I roll back just a bit here, this is essentially a similar surface to what we had in the last example. There are explicitly modeled transitions. These are just surfaces that are defined here to manage those blends between the faces. But what we're doing is we're using that geometry to manage that transition. So you can see here, I have a projected curve. And this projected curve is actually used to define the point that I want to trim back. It's kind of the point where this transition begins. And so I've created a parametric curve, but I'm really just using the parametric curve to define the point that I want to define to start that transition. And then I'm using the isoparametric curve feature to actually create the curve that will be used to generate, in this case, a bridging curve. And the reason I stress this, and you'll hear me say this at a handful of points, is you want to avoid using projected curved edges if possible. In other words, you project a curve, maybe you split the geometry around a projected curve, and then you use that downstream. And it's just the nature of projected curves is they tend to create very messy edges. And so one of the more common things that we see in surface modeling is, use a projected curve, project onto a surface, split using that projected curve, and then build on top of that, split edge using a series of features. And really recommend avoiding that if possible. If you look at the resulting edge using a curve analysis, which I'll show you in just a moment, you'll see that they tend to create very messy, kind of not very clean resulting trimmed edges. And so when in doubt, and it's possible, use isoparametric curve when you can, because the isoparametric curve is actually at that surrounding geometry. It's not a projection onto it. It's actually using the geometry of the surface itself to define that. And so in this example, it's actually a common workflow where we use projected curve just to define where that point is. And then we use the resulting point to generate an isoparametric curve. And the resulting geometry, this edge that's defined with the isoparametric curve, is much cleaner than if we had used, some other projection technique. So one big tip that I have for you, when in doubt, try to use isoparametric curves in favor of projected curves to split geometry. The resulting curve is a lot cleaner. So that's essentially what we've done here. We've taken that slab model that you saw just a moment ago. We've trimmed it back using a combination of projected curves and isoparametric curve. And now we need to build the transition or the blend between these two surfaces. And to accomplish this, like I mentioned before, very important, we use bridging curves. As you can see, here's bridging curve 1. Zoom in a bit. This is a transition between these two faces. And we get that single span Bezier curve that has a smooth transition between the resulting faces, and importantly, will parametrically update, right? And we built a handful of these. Essentially, what we're doing is building a handful of bridging curves, 3 in this example, that define the transition, a wireframe layout of that transition. And so even at beyond those initial stages of building kind of the wireframe of the overall shape, you're going to use wireframe layouts in a lot of different places. And blends and bridging curves are very good examples of that, where you're going to build a handful of bridging curves that define the boundaries of the blend, and then use that to build a boundary surface result. And so very easy for you to construct continuous, in this case, surfaces using something like a bridging curve. Now, not to dive too deep into bridging curve, because you could spend a fair amount of time on bridging curve alone, but it's a very powerful feature that has really excellent matching options. And so when you're really concerned about continuity between surfaces or between the surrounding geometry, this is one of the tools you want to do and use. And it has, of course, match pit, position, and tangency. It also has curvature continuity, right? And flow, a true G3 continuity. So if you're really concerned about the transition and smoothness in the transition, bridging curve can be a very powerful tool to adopt in these kinds of workflows. Now, I don't want to spend too much time on it, but if you haven't already dived into bridging curve and you're really looking to do some advanced surface modeling, bridging curve is going to be, I promise, one of your favorite features. So that is bridging curve, and using bridging curve in situations to manage blends. And so now we've built our wireframe. We build the slab surfaces on top of it. We trim back those slab surfaces, and we use bridging curves to build that wireframe layout of the blend. And then we can use tools like boundary surface in this example to build those boundary surfaces. But again, we're really building all of this on top of that wireframe layout of curves, whether those curves are bridging curves or control point curves, or even 2D sketches like Bezier curves in a 2D sketch. They're all applicable, but focus on the curves. And I think that's one of the biggest messages that I would take away from today. All right, jumping back to our slides. I mentioned this just briefly, but you really want to, when trimming, be very specific about what you're using to trim with. And I mentioned an example of this, avoiding the projected curve. And I'll show you an example of kind of what the resulting geometry can look like in kind of a worst case scenario when using projection and then split. Like I mentioned before, it tends to create kind of messy edges. Use isoparametric curves when possible. Right? I showed you that example. We're really just using projected to define the point where that transition starts. And then we're using isoparametric curve to actually generate the curve that will be used for the resulting bridging curves and subsequent boundary surfaces. So keep in mind, when you're building geometry, in general, be careful of project and split, using projected curve onto a surface and splitting with that surface. I'm not saying it can't be used, but you just want to avoid those kinds of situations when possible. And frankly, isoparametric curve is a better tool to accomplish that same end result. So another very important tip in this kind of same sphere is you want to avoid, when possible, building lots of subsequent features based on a trim or after a trim, but especially a trim that was built using like a projection. Because what you're doing is increasing the likelihood that there's a downstream problem. And we all know when you have a downstream problem, if you go back way up in the feature list and make modifications, you can have this potential to generate all of these downstream problems as a result of that. So one big bit of advice is be cautious about building on top of trimmed edges, and very deliberate in when you do it, and try to avoid it if possible. In general, I think that you'll end up with a lot cleaner models if that's true. So next tip, and this is an important one, and I would say this about any surface modeling that you do, and it ties very much into the theme of not building too far into the model before understanding you have a problem. And that is diagnostics. As you're building, Onshape has a whole suite of diagnostic tools: dihedral analysis, curvature maps, reflections, flows across boundaries. You can determine that. You can define the number of CPs, the control points, and the location of those control points within a surface. There's even a custom feature that allows you to do that. But the most important tip that I would give you is constantly be diagnosing the surfaces and the curves that you're building. And some of these tools you can just leave on, and I would recommend leaving them on. Zebra stripes, for instance, if you're concerned about continuity, you can just leave that, on the curvature maps as well. And you can make modifications while those are active, which is a really powerful tool for making sure your transitions are smooth or your curvature is what you're expecting. But the thing you want to avoid is building lots of features on top of geometry that is, for whatever reason, not what you want. And that's just, parametric CAD in general. But if you have, a trimmed edge that has, all these jagged definitions to it, and then you start to build a whole bunch of features off of that, and then later realize you have to trim or change that trimmed edge, you have a lot of cleanup work in redefining the parametric relationships between those subsequent features and the trimmed edge. And that applies to everything. If you don't have a smooth transition between the two faces, and then you go build a dozen features on top of that face, and then you realize later on that it's not curvature continuous, or it has a sharp transition in an area where you weren't expecting, then you have a lot more work for yourself than if you had run the diagnostics, or viewed those problems before building subsequent features. So test early, test often. I think, Greg has a slide in here, measure twice, cut once. And that analogy absolutely applies here. Measure and diagnose as often as possible, and know that what you're building on top of is solid and is what you're expecting. So where do we get to these tools? Well, the thing I would point to is all of your analysis tools are in a little icon in the bottom right corner. I'm not going to go through all of those in depth just for the time's sake, but curve and surface analysis, you can select curve and surface analysis and then select a series of edges and view the analysis of those. You can find U and V curves, inflection points, view the curvature combs associated with those faces, and you can leave this on, right? And so you can continue modifying it and have that open. That's an important one. Another important one is zebra stripes, managing those transitions. I showed you the curvature continuous transition in my bridging curve. This is kind of your visual cue that is in fact resulting in a smooth transition between those two faces. So zebra stripes is one important one, especially for understanding the transitions between various surfaces in your model. Curvature color map, also a very important one. Dihedral analysis for detecting the angle and difference on an edge between two faces, very important one. My most important tip though for you here is understand and use these tools before going on to your next step. And so if I want to know, I have G3 continuity, or G2, I should say, continuity between these two edges, how can I verify that before I move on? Well, with zebra stripes. Turn on zebra stripes and you'll see that transition pretty clearly between those surfaces. And if there's a problem here, and that should be a red flag that says, okay, I'm going to address this before I start building on, on subsequent features that are attached to this. And it's just a general tip that, you want to avoid as much as possible building on geometry that is flawed for whatever reason, doesn't match your criteria or doesn't have the transition you thought it would. Diagnostic tools like zebra stripes or curvature maps or the curve analysis, they're the tools that will help you understand that before you spend too much energy building on top of it. So that's diagnostics. I want to jump into a handful of topics around in mechanical engineering. And I say this in the broader context, a lot of surface modeling isn't necessarily, it's a lot driven by aesthetics and not as much driven by a hardcore definition of dimensions. But at some point, you're going to have to work with a team that is very much prescriptive, and the shapes need to be exact and they need to match a very specific shape. And examples of this would be like, let's say, for instance, we're building this engine cover and it has these inlets, and the inlets need to be defined based on very specific size, right? Because that's the amount of airflow going into it. And so in order to calculate the amount of airflow, they've defined the shape, and that is a very mathematically driven piece of geometry, right? It's not as much aesthetic driven as it is, there's a very specific set of variables that control the airflow. Another example of this would be, let's say you have subsequent features that need to be built for attaching this, right? So you have standoffs that locate on these hard points on other parts. Well, you can define those as well. And there is a very deliberate handoff that will happen at some point in the design process where the person responsible for creating that design, the surface modeling aspects of it, kind of the conceptual aspects of it, are then passed to someone doing the very prescriptive work. And this could be the inlets, that could be the standoffs. They're parametrically driven changes, and they tend to be very regimented in the sense that they're controlled via dimensions. And so design is iterative. There's going to be a change process that happens where the design change in the mechanical side needs to be reflected in the conceptual side, and vice versa. And so when I give the tips of building parametric intent into it, a lot of it is so that you can handle that back and forth, that iterative process of making a change to the conceptual model and not having it break the mechanical model. And I don't say that as literal two models, just passing of back and forth of modifications to the model. But it's important to keep in mind there is that handoff that happens. And so in this example, I have this hood, and in this case is actually an engine cover. It has inlets, air inlets that accommodate for the engine that's inside of it. And the inlets are controlled by a specific set of variables. And if you look into this variable table, you can see that there's offset curves, X and Y values, length, depth, width. All of these variables are used to control the amount of air going into the engine or going through these ducts and available to the engine. And so in this case, it's a combination of something that started very aesthetic, right, conceptual, where I'm using these wireframe layouts and building boundary surfaces. But now I'm getting to very kind of tactical shapes that are defined using a fixed set of dimensions. And that handoff, because Onshape is production grade CAD in both surface and solid modeling, is really just a matter of sharing it with the person that you need, and then them going in and adding the subsequent features. But the thing I would point out about this is if you've built this in a way that handles change well, tools like bridging curve or just building parametric design intent into your model, that iterative process between the conceptual part and the true mechanical engineering part will be very easy to manage. That transition between the two will be very easy to manage. So just keep that in mind. It's an important part of the process, and it's something that I think a lot of users, if built well in the early stages, will benefit in the later stages when it gets to the mechanical aspects of it. Now, there are a handful of custom features that I'd recommend. And one of them I've actually already shown to you. If you go to the Onshape forums, there's a post by Greg Brown. We've put together an awesome series of features that we're releasing as custom features first. And one of them that I really think everyone here would appreciate is the control point curve. In fact, if you looked closely in that early screenshot, the wireframe layout and the wireframe of those slab surfaces, those were largely control point curves. And it's a very powerful tool for defining the boundaries of surfaces, for boundary surfaces, or whatever it may be. And it's a useful tool for building those wireframe layouts. So control point curve, definitely recommend. If you haven't checked it out already, go to the Onshape forums. You can try it out. There's links to get it into your toolbar and start using it. There's also custom features that will tell you information around your surface. Surface eval is a custom feature that's publicly available. And you can just select a face and it will tell you the UV span, the number of control points, really helpful information for diagnosing a surface and analyzing it. There's also features for like untrim, extract, airfoil shapes, many custom features that tie into it. So not only do we have that giant list of features that I was showing you earlier, we have a long list of custom features available to you as well. And these are all publicly available. Anyone can use these. So feel free to try them out and use them wherever applicable. So that is custom features. I want to wrap up the model section of this with just a few, what we refer to as platinum rules. That's Greg's language of platinum rules. And it's because they're really important rules, not golden, but platinum. And the reason is because, and I've said this a few times, curves are everything. So really concentrate on the curves because everything is built off of those curves. And as a result, you really want to focus on single span curves, fewest number of control points possible. All of those things will lead to smoother surfaces, designs that update better in design intent. So it really is the foundation of good surface modeling is focus on the curves and how you generate those curves. Even the nuance that I was showing you a moment ago of using isoparametric curve to split rather than a projected curve is another curve tip, because we really want the resulting geometry to be as smooth as possible, as clean as possible. And you know, one of the tips that I have for you is if the curves are not what they should be, then it doesn't matter what else you do. You know, all the little tools, the patches and fills and things like that you do to build on top of that, they're not going to give you the best geometry, right? Because the core, the foundation of it all is really built on something that isn't well constructed. And so all the tweaking in the world of all the different features in the world are not going to make up for bad curves, right? Or poorly constructed curves. So focus on curves, focus on curves, focus on curves. I say that a few times because I think it really is that important. If you spend the energy there, it saves you so much energy later on. Also, this is Greg's comment, measure twice, cut once. I think it's a good analogy. When you think about building curves, you constantly, and surfaces, you constantly want to be diagnosing or analyzing those. So use the curve analysis or the curvature maps or the zebra stripes. Leave those on, you know, or turn them on and off. Use them constantly as like a check before you move on to your next step. And if you could do that, then you eliminate that possibility of finding a problem that's 5 features downstream that you have to go back and fix later on, and then fix the relevant, you know, references that need to be reconstructed. So measuring and diagnosing curves and surfaces as you're building them is probably one of the biggest tips that I can give you. Don't move on before you know what you have in the last step is exactly what you want. And, you know, the analogy, if you see something, say something. If you see a problem, fix it there. Because if you don't now and you put it in the back of your mind and continue on, you're creating more work for yourself later. And that's probably one of the biggest tips. We've seen it a lot with surface modeling is there's a practice that's implemented in the model, and then lots of things are built around that. And then you later realize that was probably not the best way to accomplish that. You know, that curve projection or fill that was built on top of. And there's lots of those kinds of examples. The last platinum rule that I would point out is flex your model. Don't be afraid to change it. I think one of the biggest things that I personally have seen with really well-built models is they actually can handle change, even change that wasn't originally intended or built, you know, with that intent in mind. It's just because of the nature of the constraints and the tools used that they built it in a way that makes it flexible. And the thing I would say about a lot of design is you don't always imagine what could happen to it in the future, but sometimes it does. And we'll talk to a lot of people who say, well, I didn't imagine it changing, but it did. And it did because, you know, design process is iterative, the mechanical engineering team needed their own changes, whatever it may be. A lot of times you may not see the need for change until it arises. And then if you haven't built the design intent in to handle those changes well, you've created work at that point, and extra work, because there's lots of references that need to be reapplied if you make dramatic changes early on. So flex your model. What I mean by that is make changes to it and see how it behaves, see how it fails. Does it fail in a certain way at a certain point when I reach a certain dimension? And am I ever going to reach that? You know, I think making modifications to a model is one of the easiest kind of go, no go tests to have you build good design intent. And, you know, it's not possible to build, you know, every model is going to regenerate perfectly no matter what change you make to it. But you want it to be robust enough where you're going to make common changes and not have to regenerate lots of features as a result. Now, if you didn't see our last seminar on this topic, all about parametric design intent, you know, building the best parametric models, I highly recommend it, because everything that's said there also applies to surface modeling, like all the variables and parametric expressions, and just properly reflected design intent is equally important in surface modeling, maybe even more so. So don't hesitate to flex your models and make those changes. So now I'd like to wrap things up. I have about 11 minutes. I'd like to wrap things up with a quick, yes, we'll call it a speed run of quick tips. And these are just quick tips for those that are perhaps new-ish to surface modeling and are just looking for techniques or tools that they're going to need to build these kinds of surfaces or geometry. And the first tip that I have for you is composite curves. Composite curves combines curves or sketch entities or other edges into a single curve. And so if you need a curve that is the composition of edges and curves and sketch geometry, composite curve is the tool for you. One thing that I think a lot of people don't realize is you can actually use composite curves to extract edges of existing surfaces, which gets really neat when you start to extend those surfaces or retract those surfaces. So just keep in mind, it's a great tool for combining geometry, combining edges, sketches, and curves. It's also a great tool for extracting edges of surface models and then modifying them, retracting or extending them. And another tip that I have for you is you can create multiple at once. So you don't have to create one independent composite curve feature for every composite curve that you intend to create. You can create multiples at once. Saves you potentially a lot of actual features in the feature list. The other tip, and I kind of alluded to this in the last one, is you can trim curves, of course, but you can also extend them. And it's the same feature. So if you go to trim curve, you click trim curve in your toolbar, you'll see at the top, there's two options. There's an option to trim and there's an option to extend. And not a lot of people are aware of that. You can use trim curve to extend a curve. And so maybe you grabbed an edge, you convert it to a composite, and then you use trim curve to extend that edge and create a new boundary for geometry. One other neat thing about the trim curve is you can build design intent. You can say this is trimmed up to an entity. And so I can extend a curve up to a face or up to another point. And like the last tip, it can handle multiple at once. So you can go through quite a few curves and extend them or trim them all simultaneously. All right, now projected curves. I gave some warnings around projected curves earlier, and I think those stand true. You could use projected curves for two sketch projection. That's awesome. Take two sketches, project them, and you have a projected curve. You could do a curve on a face, sometimes referred to as a drop curve, where you take the geometry and you project it onto a face. And that's directional. You have a normal definition that you can define for projected curves. But just be aware that projected curves always create a multi-span curve regardless of the underlying geometry. So, the rule I gave you earlier about using single span curves is this it's something you want to be aware of. And that's why projected curves always come with a little bit of a cautious note around them. And, I showed you this earlier, but you can use projected curves to define endpoints that are then later used for things like isoperimetric curves. So you don't necessarily have to use the whole curve. You could just use the points that are associated with the curve for subsequent features. And I think that's actually one of the more common scenarios, the one I showed you earlier, where you're using projected curve just to define where that transition starts, like the point where it starts. And then you use an isoperimetric curve to actually generate the curve that will split the geometry and be used to define the bridging curves later on. So just be aware, using projections is great for certain scenarios, but using projected curves and then splitting and then using the resultant split edge to define other geometry is a practice that we've seen that it can lead to problems, and it can lead. You should be cautious when using it. So projected curves definitely have their place. I think they're useful for defining those endpoints and other scenarios. I don't want to make it sound like they have no other place besides that. But for advanced surfacing, where you really care about the cleanliness of the resulting geometry, you want to be cautious with projected curves. Now, the question that commonly gets brought up, and I want to take a moment to address this, is, well, when should I use boundary surface? When should I use loft? And when should I use fill? Well, I think the simple answer to that is if you can use boundary surface, you will probably end up with the cleanest surface, right? Because boundary surface isn't directional. Like loft is directional. It has a start and an end, right? And you're passing through profiles that go from that start to that end. So it has like a left to a right or a top to a bottom. A boundary surface doesn't have that. So it's really unaffected by like the UV direction definition between the two. Whereas loft has kind of like a sweep direction, right? A direction that it goes, and you define those interior paths. So in general, if you have the option, right? In this case, we have two examples. There's a transition on the left and a transition on the right. You will end up with a cleaner surface using boundary surface versus loft. Now, the only real reason I think to use fill going beyond that is when you have n-sided patches, right? So it's not a four-sided patch. And in that situation, fill is the tool you'll need to use. But I think oftentimes it boils down to, do I use boundary surface or do I use loft? And I think the directionality of it makes a difference. Does it have a strong correlation to direction? If it doesn't, you will often be better suited with a boundary surface. And the screenshot that you see there on the slide really highlights that. The left is a boundary surface, the right is a loft. And what you'll see is it's creating lots of little cross sections along the profile. They're not even evenly spaced. So we talk about good flow of control points, evenly spaced control points. You can see the image on the left, evenly spaced control grid. The image on the boundary surface on the left, evenly spaced. The boundary surface, the loft on the right, not so evenly spaced. And a lot more computationally intensive as well, right? So performance is a real reason to use boundary surface over loft in situations where that makes sense. So next tip, create panel gaps. It's very common, especially in injection molded parts where you have multiple pieces that kind of nest together in plastic pieces. Well, you tend to model that as one, and then you split it, and you split using a combination of tools. And the most common combination of tools to create those panel gaps is to create a bridging curve that defines the transition, project that curve, split the face with that curve, offset that split, and then use a delete. And that combination will give you the cleanest separation between those two. Now, as I mentioned before, surface modeling is really about, there's aesthetics drive a much bigger part of the discussion than a traditional prismatic, mechanical engineering focused part. And so one of the biggest benefits that I found is actually using final in the bridging curve feature, really any feature in Onshape, but especially in surface modeling features, because you can manipulate the curve and manage that transition. So in this example, we've created this gap between the surfaces using the combination of tools that I showed you earlier. But the bridging curve really controls the overall shape of the transition between the two. So if we edit bridging curve, turn on final, and start manipulating that curve, we can very easily play with the aesthetics of that transition or that gap and get it looking exactly the way we want. So the big tip, use final. Final can be a really useful tool, especially if you're just grabbing and manipulating and seeing what you like. Final is kind of key because you don't have to move, regenerate, look at it, edit, move, regenerate, look at it. You just click final, manipulate, and it updates in real time. All right, another tip, use tangent edge display all the time. And this is one of those things I just recommend leaving on. So when you go to tangent edges, you can see the definition, tangent edge display. You can use it as phantom. Phantom is a good way of leaving it, but that gives you the idea, it gives you the boundaries for those surfaces. And having those on when building surface models is really advantageous. Just the ability to constantly see those and have awareness of those boundaries is especially important. And in the same kind of vein, highlighting boundary edges is a really important one, especially for surface models that don't necessarily have a thickness. You can define where those boundary edges exist. And that's especially useful if you're combining or building surfaces on top of each other. Highlighting the boundary option or edges is an option that I think is good to just leave on, right? Especially if you're doing lots and lots of surface modeling. Use variables. And I mentioned this before, but use variables to control everything if possible. Like in this example, we're using variables to control not just the distance of an offset for a surface, but also the direction of the offset of that surface. And so you can build all kinds of neat logic into variables and features that make your design intent much more clear, make the design much more robust in the face of change. So I highly recommend use variables, use expressions. If you haven't watched our past seminar on that topic, our first Mastering Design Complexity webinar was all about design intent, and we covered a lot on variables and expressions. I definitely recommend checking that out. It applies equally to surface models. All right, so some final productivity tips. Use shortcuts whenever possible. There's a long list of keyboard shortcuts. I won't have the time to go through them now. I'm running out of time here. But use shortcuts. Use the shortcut toolbar. This is actually a screenshot of Greg's shortcut toolbar. And it's an example of all the various features that you commonly use. So I can't recommend this enough. Use keyboard shortcuts, use shortcut toolbars, all of those things. Even the analysis tools and the diagnostic tools are easy to turn on and off with keyboard shortcuts. And that's one that I think that you'll use quite often. So when it comes to building robust surfaces and power users in general, shortcut toolbars and keys are everything. Explore the custom features. I've only mentioned a handful, but there are lots of custom features out there available to you. You could also import images. We didn't show this today, but you can actually insert an image into a sketch and use that to trace your geometry. And so if you're working with a conceptual design that was created by industrial designer, for instance, you can take all of that data and drop it in as an image into a sketch and use that as the foundation for building your geometry, your wireframe layout, for instance. So explore that. Use sketch image, and that's the feature you want to look for. It's called sketch image. Import those images into the document, insert them into the sketch using sketch image, and you're off and running and building the geometry that you want to trace over. I showed you this earlier, but use colors and for sketches and curves. Delineate using colors. And you could delineate for sketches and curves. You could delineate based on features. You could delineate it based on a whole bunch of things, but it's an organization technique because as you start to build more and more complex surfaces, the wireframe becomes more and more complicated. And as the wireframe gets more complicated, if they're all the same color, it can be really difficult to understand what's what. So using colors as an organizational tool is a huge tip to have. One that I didn't mention and is really valuable, one thing I think a lot of people don't consider, you can actually use Render Studio as a tool for diagnostics of surfaces, which I think is really cool and just something that a lot of people don't think about. You can bring in your model into Render Studio and analyze those transitions with real lighting, which is just super cool. And I think not a lot of people consider a kind of core part of surface modeling, but they perhaps should. Use Render Studio whenever possible to really understand those transitions well and put them under the light, literally, and see, is it as smooth as I thought it would be? So those are some final productivity tips. I know I'm running a little long. Why should I care about this? Well, there's an analogy in the world of garbage in, garbage out. If keep that in mind, if you're building any kind of geometry, but especially surface modeling, if the input isn't great, then the output isn't going to be great. And so that's why we focus so much on curves and building that strong foundation, because if the curves aren't built well, the surfaces surely won't be built well. And it doesn't matter what patches or subsequent features you build on top of it to make up for that, it won't matter. So garbage in, garbage out is an analogy that exists in lots of places, very important in surface modeling. Connectivity, you want smooth transitions between faces. You want to minimize or control the creases and the flow and the shape of the geometry. That's why you should focus on this. Also, if you're bullioning, offsetting, thickening, the success of those features is really dictated by the cleanliness of your surface. And we run into countless situations where you can't bullion, you can't offset, you can't thicken because there's problems with the underlying surface model itself, right? Geometry problems. And then obviously downstream, CAM, simulation, all the downstream applications really rely on well-built geometry. And you can introduce all kinds of problems that are kind of manufactured problems because the surface is itself not well built. And that makes generating toolpath for it difficult. It makes running it, mesh for simulation purposes difficult. So it creates lots of downstream problems you should care about. And finally, performance. You want the fastest regenerating model possible, and you want the cleanest regenerating model possible. And that's why these techniques are really valuable. I mentioned earlier things to be careful of. This is an example of a transfer. This is a trimmed edge using projected curve, I believe. And I just wanted to show the surface analysis of the surrounding edges. Look at the jaggedness associated with that. This is an example, by the way, posted in the forums. I'm not trying to call anyone out. This is something we see commonly. But it's an example of the resulting curve that comes from projected curves and how that can create really, not what you're looking for in terms of cleanliness of the edge and continuity and curvature. So, these are the things that you really want to be thinking about as you build your model and constantly reevaluate. All right. So I have run out of time. One final note. Using the classic surfacing approach to model complex concepts and detailed products is possible in Onshape. And the thing I would stress is the significantly enhanced tool set gives you a lot of control. Running back to that early slide, 38 improvements in just the last 2-ish years. And that was building on top of already a very robust tool set. So Onshape's surfacing models, surfacing tool sets are really very well-rounded. And I think that if you haven't dived into them recently, I highly recommend it. One last comment I would add, if you're interested in a follow-up from any of our sales team at Onshape, please feel free to type in +1 in the comments, and we'll do our best to reach out to you. All right, everyone. I want to say thank you, everyone, for joining, and we'll see you next time.